Today we are going to do the third application of the Gauss's theorem, that is the electric field we are going to find out, that is due to a uniformly charged thin spherical shell. Consider this as a thin spherical shell having O as the center and R is the radius of this thin shell. It is having uniformly distributed positive charge around it, and we are supposed to find out the electric field due to this thin spherical shell, first at the surface of the shell, second outside the shell, and third point is inside the shell. So at these three positions we are going to find out the electric field, and we'll be using the Gauss's law to find it out. Now, to find out the electric field intensity due to this spherical shell outside its surface, let us consider a Gaussian surface around it, that is at a distance say small r from this center to this say point P. And at point P, if we consider a small area element dA, the electric field will also be pointing out in the same direction in which the area element is there. Now, the electric field intensity at P point due to spherical shell is find out the small electric flux element at this point, that is the dot product of electric field and the area element. Since both are pointing in the same direction, so it is dA cos of 0, and integrating the above equation for the whole Gaussian surface, for the total flux for the Gaussian surface we have since electric field is uniformly distributed, it is a constant quantity, it can be taken outside, and the total flux is equal to the total area of the spherical shell, that is 4 pi r square, and mark it as equation number 1. Also, according to the Gauss law, the electric flux is given by 1 upon epsilon naught times the charge enclosed. So phi is equal to q by epsilon naught. If sigma is the surface charge density of spherical shell, then sigma is equal to q upon 4 pi r square for this spherical shell, and from here the charge is equal to sigma 4 pi r square. Using this value of q in the above equation, we have phi is equal to sigma 4 pi r square upon epsilon naught. Now mark it as equation number 2. Now the electric flux can be equated from equation number 1 and equation 2. Equating equation 1 and 2, we have E 4 pi small r square is equal to sigma 4 pi r square over epsilon naught. From here we get electric field intensity sigma by epsilon naught 4 pi r square over 4 pi, 4 and pi cancels out. We have electric field intensity sigma by epsilon naught r square over r square. So this is the electric field intensity that we have found out the relation at any Gaussian surface that is lying outside this shell, where r is the distance, small r is the distance from the center to any point on that surface, and capital R is the radius of that spherical shell. So this expression is not only for the point that is lying outside the spherical shell, rather this is the formula to find out the electric field intensity at a distance r from the center of spherical shell. So with the help of this formula only, we can find out the electric field on the surface of the shell as well as outside the surface of the shell. If we will find out for the surface of the shell, then this r will come back to the point, this one only, and here small r will be equal to capital R for the spherical shell lying on the surface of this. And if we consider inside, then this r will get smaller. So let us find out the electric field using this formula. Outside we have found out, inside and on the surface of the shell. Now the second point, to find out the electric field intensity at the surface of the shell. In that case, this P point will be lying on this point here only. So at the surface of the shell, R reduces to capital R, and the value, this formula, E is equal to sigma epsilon naught R square, since R becomes equal to R at the surface, so it will also be R square, and electric field intensity is equal to sigma by epsilon naught. So if you look for the expression when it is outside, then electric field intensity is a function of the radius as well as the distance from the center to the point where we are going to find out the electric field intensity. But if we are talking about the surface of the shell, then electric field intensity is a constant quantity that is having the ratio surface charge density to epsilon naught. And in the third part, for the point P lying inside the spherical shell, in that case, let us draw a Gaussian surface with distance, say, r dash. Now if we look at this Gaussian surface, it doesn't enclose any charge, and because of that, here there won't be any electric field inside this shell. According to the Gauss's theorem, phi equal to E 4 pi r square, this will be equal to 0, or electric field intensity is 0 if the point P is lying inside the spherical shell. So these are the three conditions that we have found out for electric field intensity. This is outside the shell, this is on the surface of the shell, and this is inside the surface of the shell. I have summed up the three electric field intensities at the points that we have discussed in the beginning. For points outside the spherical shell, the shell behaves if all the charge on its surface were concentrated at its center, and that is given by sigma by epsilon naught capital R square over small r square, where small r is the distance from the center to the point outside the shell where we are finding out the electric field intensity. And at the surface, the electric field intensity is equal to the ratio of sigma by epsilon naught. And third point, when the internal point of the spherical shell, anywhere if we take, the electric field intensity is zero. The electric field intensity is zero inside the charged shell. Now we are going to see how this electric field varies, the variation according to this formula. Now we are going to see the variation of how the electric field varies with the distance r from the center. So this is the center of the spherical shell with radius r, and along y-axis we have taken the electric field, and along axis the distance from this point O. Now this is the 0 to r is the point that will be lying inside the spherical shell, and inside the spherical shell the electric field intensity is 0. So below r, the value of small r will be giving the electric field intensity as 0. So this is the plotting of this curve for distance less than the radius of the spherical shell. And if we consider at the surface of the shell at this point r, the electric field will be the maximum and the value will be equal to sigma by epsilon naught. For example, at this point we are having the value sigma by epsilon naught. So here the electric field is going to be maximum, and that will be the constant value. So that will be a straight line. Now, if this value, the distance r increases than the radius of the spherical shell, then we have the variation according to it. If you look at this relation, sigma epsilon r, these are the constant quantities. R varies, so here the electric field varies according to the square of the distance that is taken from the point O, and here the electric field gradually decreases. Here electric field decreases and it is inversely proportional to the square of the distance. So at this point outside the shell, electric field decreases according to this relation. At the surface, electric field is maximum, and inside electric field is 0. And these things we have plotted in this curve that we have drawn, electric field versus the distance. So this is all about the electric field intensity due to uniformly charged spherical shell.